Okay, so we have a sort of a framework for solving systems of equations at this point. We have this idea that we're going to view a system as a single thing. We're going to focus our attention on the system and not think of it as just a bunch of individual equations. And we have this process, this collection of processes called elementary row operations. And remember, elementary row operations are really just elementary equation operations. The idea is you have a system, you turn it into a different system. But importantly, because elementary row operations are reversible, the system that you turn into another system, those two systems will be equivalent. They have exactly the same solution. So our framework or process that we're allowed to use is to take our system and apply elementary row operations however you might like, however might seem convenient, and go ahead. Now, here's the problem. Where are we going? Right? We have a process that we're allowed to apply, but we need something to aim for. We need a target. And that target is called reduced row echelon form. Reduced row echelon form is a sort of a structure. It's a collection of rules that a matrix might satisfy, and it turns out that this makes for a great target. Now, what is a great target? Well, keep in mind you're trying to solve a system of equations. A great target would be something that makes solving the system as convenient as possible. So we're going to see details about this in the next few minutes here. But the big idea of reduced row echelon form is that it makes solving the system as convenient as possible. Okay. All right. So let's talk about what reduced row echelon form actually is. What are these rules that define reduced row echelon form? And there are several. So we'll start with row echelon form. Matrix is in row echelon form if each row has more leading zeros than the preceding row. Until you get to the end, the last several rows perhaps might be all zeros, and of course if you have rows that are all zeros, it's not possible for each to have more than the previous because you're done. So that's sort of exempted from the more leading zeros rule. So this is called row echelon form. Okay. In a particular row, there will be perhaps a first non-zero entry starting from the left. There might not. There might be that all the entries are zero. But if the entries are not all zeros, if there is a non-zero entry, there will be a first non-zero entry. And we call that a pivot. We'll talk about why that's called a pivot at some point in the future. Okay, so with this terminology in mind, we can give the definition here of reduced row echelon form. There are three requirements. For one thing, it's got to be in row echelon form. So more leading zeros than the preceding row all the time. Secondly, the pivots have to be 1. So the first non-zero entry in each row has to be 1. And wherever that pivot is in any row, that pivot would then have to be in a column, and all of the other entries in that column have to be 0. Okay, so these are the rules. By the way, a column that has a pivot in it, we call that a pivot column. Okay, so any matrix that satisfies these three rules is said to be in reduced row echelon form. Now, a side note, if you're talking about a system of equations, we can talk about the system being in reduced row echelon form. Specifically, when we refer to a system being in reduced row echelon form, we're talking about the coefficient matrix being in reduced row echelon form. Okay. All right. So there's some neat facts about reduced row echelon form. These are not obvious. These are things that have to be shown, and we will not show these properties, all of them anyway, in Math216, but we will make use of these facts. And the first one is very important. Every matrix can be put into reduced row echelon form by elementary row operations. This can always be done. Again, there's some discussion as to exactly why that's true, but it is true. And so, good news. It's a target that we can hit. It's not impossible to get there. Okay. Secondly, for any given matrix, there is a unique reduced row echelon form. And that's kind of nice. In other words, if you and a friend start with the same matrix and say, okay, well, here, let's you put it in the reduced row echelon form, I'll do the same, you can check your answers, because it's not possible to have both satisfied all these rules unless you, in fact, get exactly the same reduced row echelon form matrix. So it's not just that it's possible, it's uniquely possible. Okay, again, that's not immediately clear, but it can be shown by methods that we won't talk about in this course. Finally, and this is something we're going to make a lot of use of, and this is, again, why we care about reduced row echelon form. Once you have if you take a system and you put its matrix into reduced row echelon form, there's a convenient means of getting the solutions at that point. Okay, so we'll talk about that in a few minutes. Now, first, I just want to go back to the rules, and let's look at some matrices and see what does it look like. What does it mean for all these rules to be satisfied? So here we go. This matrix here is in reduced row echelon form. Now let's check the form. Let's check the rules. Excuse me. See how this works. Okay, so this first matrix. Let's count leading zeros in these three rows. So the number of leading zeros in the first row. How many zeros before I get to a non-zero number? Well, there aren't any. There are no leading zeros. In the second row, there's the only leading zero. Now, we don't count that. That's not a leading zero. Right? Leading zero just means zeros that you get to before the first non-zero entry. So here there is one leading zero. Here there are two leading zeros. And notice that these numbers are increasing. 0, 1, and 2. So this matrix is in row echelon form. All right. Now, second rule. Are the pivots all 1? Well, let's identify where the pivots. The first non-zero entries are these. And sure enough, they're all 1. Okay. Let's keep those pivots identified. Okay, lastly, let's look at the pivot columns. Let's look at the columns that have pivots in them. Well, this column has a pivot. That column has a pivot, and that column has a pivot. Is it the case that in those pivot columns, that other than the pivots themselves, the entries in those columns are all zeros? And of course, yes, clearly that's the case. Okay, so this matrix is in reduced row echelon form. Now, you'll notice this is a familiar matrix to some of you who might have seen at some point in the past the thing called the identity matrix. So conveniently, the identity matrix is in reduced row echelon form. It's important to realize that it's not always the identity matrix. So plenty of other matrices are in reduced row echelon form. So for example, let's count leading zeros. 0, 2, 3, 3. And this is increasing, at least right up to the point where they are all zeros, and that is allowed. So this matrix is in row echelon form. Let's identify the pivots. There's the pivots. Notice there are no pivots in the third and fourth rows because there are no non-zero entries at all, much less a first one. Okay, the pivots here, all 1. So that rule is satisfied. Finally, here are the pivot columns. Are the other entries other than the pivots all zeros? Yeah, they are. So fine. So this matrix is in reduced row echelon form. Now, a lot of students get thrown and think, it just feels like that 3s shouldn't be there. Isn't reduced row echelon form supposed to take a matrix and kind of, whittle it down to, get everything sort of as organized as possible? And that extraneous 3 just doesn't seem like it ought to be there. Well, it's fine. It does not contradict any of the rules. And it is, in fact, important as part of the reduced row echelon form. So that's fine. So this matrix is in reduced row echelon form. Lastly, this one, increasing number of leading zeros. Right? 0, 3, increasing, done. Pivots are there and there. The pivot columns are all zeros except for the pivots themselves. This matrix is in reduced row echelon form, despite all of this extraneous seeming junk that appears to be there. That's not a problem. It's fine. Okay. All right, so that's what reduced row echelon form looks like. Okay. A little bit of terminology. Keep in mind we've talked about pivot columns. So if the column contains a pivot, that's a pivot column. Well, don't forget, remember as well that columns correspond to variables, right? In our matrix shorthand, a column is where we put the coefficients, all of the coefficients for a given chosen fixed variable. Okay, so a variable whose corresponding column contains a pivot, we call that a pivot variable. Okay, so for example, up here, if these were columns corresponding to x1, x2, x3, then x1 and x3 are pivot variables because their columns have pivots. x2 is not a pivot variable. Okay. All right. So what do we call those variables? Other variables whose columns do not contain pivots, we call those free variables, and we'll see momentarily why we call them free. So x2 is a free variable. Okay, a bit of terminology we have to lay down. And with that, we can address the big question, and that is, what is it that makes reduced row echelon form so convenient anyway? What an arbitrary list of rules about leading zeros and ones and zeros and this kind of stuff. What makes that so convenient? And this is the most succinct answer to that question as I see it. And it's because you can always solve for the pivot variables in terms of the free variables, only the free variables. Okay, so let me show you an example, and then we'll see also why this is such a big deal. Let's look at this system. Now you'll notice this system's already in reduced row echelon form. And let's solve for the pivot variables in terms of the free variables. Well, don't forget our pivots are there and there, so the pivot variables are x1 and x3. Don't forget that these correspond to equations. So this is actually an equation that says x3 equals 5. Okay. Likewise, that is an equation that says 1x1 plus 3x2 plus 0x3 equals 2. And if you solve for the pivot variable, which is x1, in terms of the free variable, which is x2, you get that. So what I've done here is I have solved for the pivot variables in terms of only the free variables. Okay. And if you then write that down, keep in mind what we're looking for. We're looking for solutions. I'm looking for what x1, x2, and x3 should be to solve that system. And if you just plug in what you've just found, so specifically x3 equals 5, and x1 is equal to 2 minus x3, let's plug that in, and this gives you all of the solutions. This gives us exactly the solution set to that system of equations. Okay. The idea is, and here's why we call x2 a free variable. We call it a free variable because it's allowed to be anything. x2 doesn't have to be anything in particular. Plug in any value of x2, and then now once you've picked x2, then that tells you what x1 has to be. And it's already, even without that, determined what x3 has to be. So the pivot variables are not free. The pivot variables have to do what they're told. They are dictated. Their values are dictated by the values of the free variables. But the free variables are under no such constraints. They can be anything. Okay. Now, how do I know that these are actually solutions? Well, this is something you can actually see immediately from our process here. How do I know that this equation is satisfied? Well, because it says 0 equals 0. That's always true. That's not a problem. Asterisk. We'll come back to that in a minute. But how do I know that this equation is satisfied? Well, because that corresponds to the variable x3, and I have chosen to make x3 be whatever it has to be to satisfy that equation. I deliberately, by solving for x3, by solving for that pivot variable in terms of whatever it has to, and the free variables perhaps, but aren't there in this case, I'm guaranteeing that that equation is going to work. Okay. How do I know that this equation is going to work? Well, because I arranged it that way, right? I chose x1 to be whatever it would have to be to make that equation work, because I solved for that pivot variable x1 in terms of the free variables. Okay. So, loosely speaking, these are solutions because we arranged it that way. Okay. All right. Now, do be careful about the difference between the roles of columns and rows in this little process. It's tempting. Students have a tendency to look at these rows and think that that somehow tells you what these are supposed to be, and that's not the way it works. So specifically, variables correspond to columns, right? So somehow this third column is what's telling me what the third variable has to be. Now, here's how that works. In that third column, there happens to be a pivot. This is what you then might call that corresponding pivot equation. That pivot equation gives you this. In the second column, there is no pivot. There's no pivot at all. Therefore, there's no pivot equation. Therefore, there's no pivot in that column that I've solved for, and therefore there is nothing to say there. So there are no constraints at all. And because this is the x2 column, no constraints means x2 can be whatever it wants. So there is no free variable equation. That's kind of the point here. Free variables don't have equations. Right? Okay. And then let's see, what can we say about x1? What do we deduce about x1? Oh, I forgot to put the little thing there. x1. Well, x1, there's a pivot in the x1 column in that row, which gives me this equation. Right? So yeah, for each one of the variables, there is a corresponding formula for what those variables have to be, but they don't correspond in the same way to the equations in the system. There is an x1 equation. There is an x3 equation, but the x3 equation is not the third equation. Pivot variables have equations, free variables don't. Okay. Alrighty. So this is how we turn a reduced row echelon form system into solutions. This little process right here. Okay. Now, a couple of questions. I've made the assertion that this gives us the exact solution set. How do I know that? Well, it all ultimately boils down to this idea here, that in reduced row echelon form systems, you can always solve for the pivot variables in terms of only the free variables. Okay. So, how does that answer these questions for us? How do I know? We worried about this earlier. How do I know that everything I find by this method will be a solution? no matter which free variables I plug in? And the answer to that question is very simple. It's because I know for sure that all the pivot equations are satisfied. And of course, all the equations are pivot equations. All of the equations, anyway, other than this at the bottom, which we'll talk about in a few minutes. But all of these equations have pivots in them. And I know that they're satisfied because I solved for my pivot variables in terms of my free variables. This fact, this property of reduced echelon form is how I know that everything I get is a solution. Okay. Here's the harder question. How do I know that I will have found all of the solutions? Right? I've found some solutions. I mean, this is a bunch of solutions here. Right? If x2 is any value, I mean, there's infinitely many different values that x2 could be. It gives me infinitely many ordered triples by this little formula. But maybe there's more. Maybe there's some other solutions out there that don't fit this form. How do I know that there aren't? Well, suppose there is such a solution, some hypothetical solution that somehow we missed in this form. Well, whatever that solution is, the free variables are going to have certain values in that hypothetical solution. And whatever those free variables are, I can use to plug in and see what the pivot variables then have to be, and I know that I can do that. I can find what those pivot variables have to be because I've already solved for my pivot variables in terms of the free variables. Right? So whatever free variables, whatever values the free variables might take in this hypothetical solution we missed, take those values, plug them in, see what the pivot variables have to be. I mean, this solution would have to have those values of those pivot variables. And what you get then is a solution that we've already found. Right? Because those free variable values are values that those free variables could be, and we've written down what the corresponding pivot variables would therefore have to be. So any hypothetical solution, we have found it because of this argument. And ultimately what it comes down to is, again, because we solve for the pivot variables in terms of the free variables. Okay. So I like to come back to this. This, plus it rolls off the tongue very nicely, this is the answer to an enormous number of questions about reduced row echelon form. Reduced row echelon form is convenient because you can solve for the pivot variables in terms of the free variables. You know you found all the solutions because you can solve for the pivot variables in terms of the free variables. You know that everything you found is a solution because of the fact that we solve for the pivot variables in terms of the free variables. So this is a really nice little distilled summary of why we care about reduced row echelon form. Okay. Now there is one little asterisk I have to come back and address, and that is contradictions. So I glossed over in this previous system. I glossed very quickly over the fact that okay, well that says 0 equals 0. Well, of course that's always true. Moving on, right? And we started talking about these other things. But what if that said this instead? Well, that says 0 equals 7. So we've got a problem here, right? If we're looking for solutions, if we're looking for values of x1, x2, and x3 that are going to satisfy that equation, and they're going to satisfy that equation, and that are somehow going to cause 0 to equal to 7, well, we're going to lose. There's no way to do that, right? There is no way to make this equation satisfied. This equation is always wrong. Right, so there are no solutions to this system of equations. And conveniently, again, these sorts of predicaments that we call contradictions are always easy to spot. Right? They are simply equations in which we have all zeros on the left, right? Which is what causes the entire left side to have to be 0 no matter what x1, x2, and x3 are. Combined by not 0 on the right. So you can find them at a glance. Contradictions are easy to spot. in the reduced echelon form system. Okay, so other than that, though, I mean, in the absence of contradictions, solve for your pivot variables in terms of your free variables. Those are your solutions. If there is a contradiction, you don't have to solve for anything. You just say, we have a contradiction, therefore this is garbage, and there are no solutions, and you're done.